Hello, this is Professor Theory. Today, I'm going to share with you guys more exercises and examples for you to understand better about the topic implicit and partial differentiation. Let's get started right away. We are going to do some advanced differentiation in this lesson. Thus far, we have done differentiation of explicit function. Explicit function has y on the left side of the equal sign, while on the right side of the equal sign are all the terms with x in it. Like the one on the screen right now. Well, we have done differentiation numerous times, so I don't think you have any problem differentiating this equation. So now, that is the answer. But implicit functions pose some challenges. It is called implicit because x and y both exist in either on the left side or on the right side of the equation. For example, take a look at the equation on the screen right now. That is an implicit function. If you want to draw the graph, then it will look like this. Interesting, isn't it? If we can come up with the derivative expression for this function, then we can come up with the gradient of the curve at any point on that slanted oval. But there is no way that we can move only y on the left hand side of the equal sign and move everything else on the right. So we have to derive it implicitly. And here's how to do it. First of all, we differentiate the expression on the left and on the right separately. But on the left, because there are three terms in there, we can differentiate them individually. So the first one, for the first term, that is x squared, that is easily being derived to be equal to 2x. But differentiating the second term is a little bit challenging. It requires product rule. So now, that is the product rule. I hope you have learned that and have no problem using it. So differentiating xy with respect to the x will give us x dy dx plus y. Now the last term requires us to use chain rule. Now we have already covered chain rule in previous lesson. I hope you don't have any problem with this. Differentiating y squared will become 2y multiplied by dy dx, and that's chain rule. And now lastly, on the right hand side, that is just a constant, just a numerical number, so differentiating it will give us 0. Now the worst part is over. What we need to do is to group them up. And remember, in the end, we want to have only dy dx on the left hand side of the equal sign, and everything else has to be moved to the right. So now we minus 2x plus y on both sides of the equation, but we still have x plus 2y that is attached to dy dx. So let's divide that by x plus 2y, and that remove everything except dy dx on the left. So now that is the expression of dy dx. The interesting part is dy dx is an expression of both variable x and y. So if we want to find out the gradient of the oval at coordinate 5, 0, what we need to do is to substitute 5 for x and 0 for y, and we get the answer of minus 2. So minus 2 is the gradient at coordinate 5, 0 on that slanted oval. Now let's go to the uncharted territory of partial differentiation. We are all well trained to differentiate a function of x, such as this one. Fx is equal to x squared minus 2x plus 3. This is a two-dimensional function. We can actually draw the graph on a piece of paper on the x and y Cartesian plane. So the derivative will give us f prime x equal to 2x minus 2. That is very straightforward and simple. But what if we have a function of more than one variable? For example, function of x and y, that is a three-dimensional function. And function of x, y, and z, and that is a four-dimensional function. We have exited our dimension realm and entered into dimension that we are not very familiar with. But this is a good start because according to some physicists, through some mathematical modeling, they found out that our universe is made of 11 dimensions. How can we ever describe 11 dimensions using our known languages? We can't. We can only model it mathematically. So if we want to talk to extraterrestrial beings, we need to learn maths. But it is not as complicated as we thought it is. Let me begin with one simple example, and I will leave it to you to think about the more complex examples. Say we have this function, a function of x and y, that is equal to x squared y plus xy squared. If we want to differentiate this expression with respect to both x and y, then we need to do it one by one. When we differentiate it with respect to x, we treat y as a constant. And when we differentiate it with respect to y, we treat x like a constant. Then we'll have two derivative expressions, and here's how to do it. First, we differentiate each term with respect to x. So for the first term, which is x squared y, we treat y as a constant, so y will retain. So x squared will become 2x. So multiply that with y, that becomes 2xy. Now, the second term is xy squared. Then we'll treat y squared as a constant and differentiate x. And because x is to the first power, then differentiate it will make x disappear. So it will left with y squared. So this is the expression of df dx when we differentiate it with respect to x. Now we want to differentiate it with respect to y. So for the first term, x squared, we will treat it like a constant, like any numerical constant, and differentiate y. Because y is to the first power, then y disappears, leaving only x squared there. And now the next term is xy squared, and we'll treat x like a constant, so x will retain. Differentiating y squared will become 2y. So multiplying that with x, that becomes 2xy. So that is the expression of the function when differentiated with respect to y. So now we have ended up with two derivative expressions for that function. We have completed partial derivative. It is not that complicated, is it? Now I want you to do some extra research, search the internet or library and find more examples about this topic. And if you master this, you will go far in your life. Thank you very much for staying with me until the end of this video. See you again.